Welcome to Operating Systems Lecture 10. So far we were looking at segmentation as a way of implementing virtual memory. Right? This notion where there is a separation between a virtual address and a physical address, and there is some translation logic that goes to convert a virtual address to a physical address. This system is called a virtual memory system, and we saw segmentation as one way of implementing virtual memory, right? Where the translation was rather simple, we just added base to virtual address to get a physical address. And we said the way it works is that there's a table which is stored in memory, which is called the global descriptor table, which contains these descriptors, right? And this table can be as large as 2 to the power 13 entries, where each of these is one entry. Each of these entries contains a base address, which will be a physical address, and a limit, which will say what's the size of this particular segment. So each descriptor defines a segment, and the program itself is going to dereference one of these descriptors using the segment selectors, which are these which are stored in these segment registers. They are CS, DS, ES, FS, etc. And they are going to dereference these descriptors here. And we also said one typical way of organizing the segment table is the following. You have some extra entries in this to store the task state segment and null entry. We can ignore this for the time being. But there will be two descriptors. One will be for the kernel's base and the kernel's limit, and the other one will be for the user's base and user limit, right? At any point of time. So at any instant of time, you'll have these two entries, in a typical operating system which is using segmentation to implement virtual memory. And what happens is typically that the kernel base and kernel limit remain constant throughout the execution of the system, right? Because they refer to the kernel's space, and the kernel always maps itself in a certain address space, and in the physical memory, and the kernel is always mapped, and it's always the same contents of the kernel that are always mapped. But the user base and user limit descriptor keeps changing over time, because context switches happen between one process to another process. So for at one instance it could be the P1's U base and U limit which are loaded in this descriptor. After a context switch, it will be P2's U base and U limit, which are getting stored in this overwritten in this particular descriptor, right? So the kernel remains constant, and the processes descriptor, or the processes, the address space which is for the user is defined by which process is currently running, and that gets swapped on every context switch, and that happens by the kernel. Both of these need to be mapped at any point of time, because as we have seen, control can transfer from user to kernel if some event occurs, like an exception or an interrupt or a software interrupt, and in which case immediately you need to dereference the kernel side of the address space. For example, the CS in the IDT table could be a kernel, must be pointing to the kernel descriptor, and so both of these are mapped. The way you prevent the user from accessing the kernel's address space is basically by having another field here, which is the privilege level. Let's call it P. So one of them will say I can only be accessed in privilege level 0, and the other one can say I can be accessed in either privilege level 0 or 3. So it doesn't. So that way when if the processor is executing in unprivileged mode, it will only be able to access the dereference through this descriptor and not others. All right. Also, typically, I said that there are 6 segment registers, CS, DS, and so on, right? And each of them could actually be pointing to a different descriptor here, potentially, right? CS could say I want to point to descriptor number 2, DS could say I want to point to descriptor number 3, and so on, right? Assuming privileges are respected, etc. And so that can potentially allow one process to have 6 different segments in physical memory, and so that can solve some of the fragmentation problem that we discussed last time. But this kind of an organization where you divide your address space into multiple segments actually complicates the programming model, because now the compiler needs to worry about exactly, does this address live in this segment or that segment, etc., and it needs to generate code appropriately, right? So typically what's done is that all of these actually map to the same segment. To give the abstraction of a flat address space, right? So the compiler can assume a flat address space, and all of these actually map to the same sort of descriptor, and so the process just sort of sees one flat address space from 0 to max, right? So it simplifies the programming model, but it has the problem of fragmentation, as we discussed last time. Now the entire process has to live in one contiguous segment. Okay. Also, there was a question last time about the GDT being too large. 2 to the power 13 entries is too large. I mean, I'm only going to use 5 entries out of these 2 to the power 13 entries. So actually, I omitted a piece of detail. The GDTR actually doesn't point to the base directly. It points to another memory location which contains the GDT base. Let's call base GDT and limit GDT. So base GDT points to the base of GDT, and limit says what's the size of GDT. So that way, you don't need to waste all the space. You can say that my GDT is only 5 entries or 10 entries, and so the hardware actually gives you a way of saying that, of specifying the size of the GDT, and the maximum value of that size can be 2 to the power 13. Okay, so you're not really wasting space in that sense. Okay, all right. So question.
Will there be any point in time when we'll be using all the space of GDT?
Will there be any time, can it happen that I use all the space in my GDT? Depends on your kernel model. In the model that I've described so far, it's not possible, right? Because the number of descriptors that you can have is actually constant, right? Just these 4 registers, descriptors, for example. So it's not possible in this model. In another model, it may be possible, in which case the kernel should have logic to handle it. Okay, but let's just live with this model and say no, it's not possible. Okay, another question.
Is the k-base and k-limit constant for all the entries?
Are the k-base and k-limit constant for all the processes? Is that your question?
Yes.
Yes.
The same, I mean.
Yeah, so k-base and k-limit don't change on a context switch. Okay, so on a context switch, the kernel remains as it is. It's the process's address space that you are changing. Yeah, one more question.
Base GDT and limit because GDTR can directly point to a physical address, and we don't need a base GDT.
Yeah, so these are actually physical addresses, all right? So these are, let's call them physical addresses for now. Base GDT is saying here's where the GDT starts, and limit GDT is saying this is where the GDT ends. That's all.
We can just have limit GDT. We don't need actually base GDT.
Now, how do you specify where it starts?
Because we have GDTR which points to the base.
No, so that I'm saying GDTR will point to this structure, and this will contain the base and limit.
We can have limit in the table itself, right? GDT.
Oh, okay. You're saying, why do I need this kind of thing? I could have, GDT could itself have some notion here which says limit. Yeah, it's a matter of, it's a matter of fact that this is how it's done on x86. But you can design something else. Okay. So it basically says that everything above this is not possible. So for example, if I didn't have a limit GDT, and let's say our hardware assumed that the limit GDT will be 2 to the power 13 always, then what will happen is the kernel will have to reserve that extra space and invalidate all these entries. So there's a certain bit in these descriptors which says this descriptor is invalid. So he'll have to say invalid on all these things. If he doesn't do that, then that space can be used for some other data structure, and if that data structure, a process can now manipulate those things, right? Because let's say there was some other data structure living in this space, and now the process actually sets his pointer to point here, then he can now access something he's not supposed to access, for example. So if there was no limit, then the kernel would have had to allocate the entire 2 to the power 13, and just to sort of not waste that space, the hardware allows you to specify a limit. Okay. So how are ubase and ulimit accessed? They are basically accessed using a virtual address, right? So virtual address in this case is basically of the form of a segment register colon some offset, and the offset could be specified in one of the modes: immediate, indirect, or displaced, whatever. In either case, CS actually goes here. So what happens is offset gets added to base, and offset gets compared to limit. right? And that's how you're actually dereferencing or accessing the GDT entries on each memory access. Okay, the user is not allowed to read this GDT directly. It's only allowed, it only gets dereferenced through this mechanism of virtual memory translation or MMU. Okay, the user cannot access these entries directly. No. In case of context switch, does the limit GDT change? You mean does UBase and ULimit change?
No, limit GDT.
Oh, you mean this? No, this doesn't change. So these remain constant. I mean, so it depends. Different operating systems can implement it in a different way. Let's say the way we are talking about it is that the GDT remains constant. It's just this entry that's changing. Everything else remains constant, right? It's just this particular descriptor that's changing on a context switch. Question.
So if limit GDT stays constant, then why do we need to store it anywhere? Like if we know the base GDT and if we know the size of GDT that is required for the entire operation, why do we need to store it somewhere in base memory?
Why do we need to store limit GDT? Because we need to tell the hardware what's the size of a GDT, right? Because the hardware that's going to actually dereference. So how's the hardware going to do this? He's going to say, let's look at the selector in CS and add it to base, right? And he's going to compare it against limit. So if there was no limit, then CS could point here, and so now it's the responsibility of the kernel to ensure that all these entries are invalid.
No, but so like the kernel will always have just six segment selectors. User will UBase and ULimit will always have just 6 segment descriptors. So basically, the size of the GDT will always stay constant, right?
Okay, let's say in our model, the size of the GDT always stays constant. Okay, so yes, absolutely.
So in that case, like we don't need to really store limit GDT anywhere. We can just like build it into our model itself.
No, so this limit GDT is a way of the kernel to tell the hardware. That's all. I mean, the kernel is not storing it for its own purpose. The kernel already knows that it's 6. It's telling the hardware that it's 6. It has to tell the hardware in some way, and this is the way of telling the hardware that look, there's only 6 entries that you should be accessing. Okay.
So in this model, the value of CS remains always the same.
CS, DS, yes, everything remains the same. In fact, in this model, when I context switch between two processes, the segment selectors remain the same. They're always pointing to, let's say, the third entry in this table, right? It's just the entry that's changing every time. Okay. But yeah, it's possible that you have, it's possible that the kernel allows you multiple UBase and ULimits, in which case the program is allowed to change between multiple things. Okay, great. The next question, the next thing I wanted to point out was that on every memory access of this type, right, let's say CS or DS, offset, whatever, what's required is CS is stored on chip. So there will be some logic that dereferences CS to get a selector, but the GDT itself, now that CS, the selector is going to get added to the base of of GDT. So but to get to the base, you need to dereference GDTR. And the base is actually stored on memory, so you actually go to memory to get the base, right? Then you add it to CS, then you get a descriptor, then you get the base from the descriptor. Once again, you make a memory access to get the base from the descriptor because the descriptor is stored in memory. And now you add the offset to the base and compare the offset to the limit. And now you do your final memory access, which is base plus offset. So one memory access had how many more memory accesses? 2 extra memory accesses, right? One for dereferencing the base, and the other for dereferencing the base of user. One for dereferencing the base for the GDT and one for base of the descriptor, right? So that sounds very wasteful, right? So what's the typical thing that's done? Caching, right? So you have already done your computer architecture course, you've seen caching. So what's done is when you execute the load GDT instruction, these values get cached on chip. So there is some space on the chip which basically allows you to cache these values on chip. Okay. And plus, the semantics of this are that if the kernel, let's say changes the base limit to something else, then it doesn't immediately get updated in the chip because there will be a lot of logic that will be required to do that. Instead, what happens is GDT, the cache can remain out of sync from the memory. So if you want to actually recache it, then you should execute that LGDT instruction again on the new base and limit, right? So it's caching, but it's not they don't remain consistent. So the cached value and the real value in memory don't necessarily remain consistent. You can reload the cache by re-executing the load GDT instruction. Okay. So what is this kind of caching? Is it write back, write through? You haven't done write back or write through cache? This is write back. Okay. Is this write through? No, it's not write through, right? Because I can actually go and write to the memory without the cache knowing anything, right? Write through basically means that I have all my writes have to go through the, so I go through the cache and I first update the cache and then all the things that I update in the cache go down. So actually I have direct access to the main memory, and so cache is actually can be out of sync. So it's not write through. Is it write back? It's not write back either, because once again I actually change the value underneath and then update it by using the LGDT instruction, right? So it's neither write back nor write through. It's it's another kind of caching where basically you explicitly invalidate or explicitly load new values into the cache, right? The cache is actually just acting as a read-only cache for so the cache is accessed in only read-only mode. The only way you write it through explicit invalidation of the old value by re-executing the LGDT instruction, or call it the invalidate instruction. It's neither write back nor write through, but it's a different type of cache. Right. Similarly, when you load values into the registers CS, DS, etc., the descriptor values base and limit get cached on chip. Right. So just like this, the descriptor values get cached on chip. So you don't actually make memory access to each time you don't actually dereference memory to get these values each time you make a memory access. You have it on the processor, cached. Once again, the semantics are that when I load it, it gets loaded into the cache locally on the processor. But if you change it later on, that cache still retains the old value, right? If you want to overwrite that old value, you need to re-execute. You need to reload the segment register using some instruction like move, let's say AX to CS, right? So when you reload the segment register, the cache gets freshly loaded. But if you change the memory underneath, the cache keeps the old value. Okay. So this is the caching model. So with this caching model, every memory access will actually make only at most one memory access, usually, typically, right? Because each time you execute this address, the GDTR's base is stored and limit is stored locally. You can add it to the selector to get the descriptor value. The descriptor value itself actually is stored in the locally, and so you can just get the U base from there, or K base, depending on whether it's a kernel segment or a user segment, and you can and you actually just go to the memory for the real physical address and nothing else, right? So this way you also have to worry about performance, and so you care about performance. What this caching model also means that the OS needs to be careful that the cached value and the memory value don't go out of sync, right? So GDT remains in this kind of model that we are talking about. GDT remains constant, so it only gets initialized once, it gets cached once. OS doesn't need to bother really. And in fact, even K-base and other descriptors are actually only remain pretty much constant. It's only this user base and user limit that are actually changing, and so on every context switch, what the OS will need to do is reload these segment registers again, all right, with that particular descriptor value, so that they actually now get the new cached values before it actually context switches back to the process. Okay. So that was segmentation, and segmentation allows you. So nice thing about segmentation or virtual memory in general is that it allows separation between physical address space and virtual address space. And now virtual address space can be this uniform address space starting from, let's say, 0 to some value, and the physical and you can place the processes anywhere you like at runtime, and the same program is going to run with assuming that it's actually running on a uniform address space. But it has problems. The first problem we saw was fragmentation. Right? So because a process's address space needs to be contiguous, if different processes of different sizes are created, then very soon my physical memory can get fragmented and I could be wasting space. So new processes may not be able to get admitted because the spaces that I have, the holes that I have are smaller than the size of the process, even though the total space I have could have accommodated that process. So it has problems of fragmentation. It has problems with things like process growth. If I want to grow a process, it's very difficult because I've already placed the process somewhere, and now there are other processes which are around this process. So now I want to grow the process. The only option that I have is either move other processes up or down, or move this process somewhere else, right? And in both cases, it requires physical copying of the entire memory of the process from one region to another in physical memory, and that's a lot of work. Okay, and thirdly, some of these problems can be alleviated by having multiple segments, but multiple segments has a problem that the programming model becomes complicated. Right? The programming model, if you have multiple segments, then the compiler has to worry about which segment I have to access, as opposed to just saying here's an offset and that's it, and doing that. Okay. So paging is another way of implementing virtual memory. All right. Here what's done is, let's say this is a physical address space. I'm going to call it PA, physical address space, PA space. All right. What it does is it divides this physical address space into fixed size chunks, right, called pages. So each of these sort of frame is called a page, right? And then it divides the virtual address space also into pages of the same size. Okay, so this is also a page, and then it has some function in the middle, f, which is implemented through a table, a lookup table, which maps a page in virtual physical address to a page in virtual address, a page in virtual address to a page in physical address, okay, and so on. So completely arbitrary mapping. Okay. So the virtual address space also, just like before, starts from, let's say, 0 to some value. Let's say, let's say it goes all the way to 2 to the power 32 minus 1, because that's the maximum addressing that you can do anyways, right? Because it's a 32-bit machine, so the maximum size of the operand that you can have for a memory address is 32 bits, because the registers are 32 bits, the immediate operand is 32 bits. Even when you execute in displaced mode, it gets wrapped around to 32 bits. All right. So the virtual address space goes from 0 to 2 to the power 32 minus 1, and the physical address space goes from 0 to whatever maximum M you have, right, depending on how much memory your machine has, whether it has 512 MB, 1 GB, so that's the value of M. Right. And this function is going to map these pages in this address space to pages in the physical address space. Okay. Now the program just works as before. Program just assumes that it has this virtual address space. It just once again it just says I want to access address vadder. I want to access an address called vadder. What happens is you say, oh, vadder is here, let's say. So you say, oh, it belongs to page number this, right? You basically do some calculation to figure out this is the page number that it belongs to, and you figure out, oh, this page number is living in this page number of physical memory. So you do that translation, and then you convert that vadder into a padder. Okay. So what's the nature of this translation? Well, let's say the page size was p, right? And let's say the page size was p, and p was equal to 2 to the power small p. So let's say p was some multiple of some power of 2, just to make things simple, because we are working on a binary machine where bits are binary, and so so if I want to convert V adder to P adder, what I'm going to do is I'm going to say V adder divided by capital P, that's going to give me my page number in virtual space. So I'm going to call this the virtual page number, VPN, right? And I'm going to convert VPN, I'm going to look up a table to convert VPN to PPN, okay? That's a physical page number. And now I'm going to say, P adder is equal to PPN into P plus V adder mod P, right? That gives you a one-to-one mapping between, assuming there was a one-to-one mapping between VPN and PPN, this gives you a one-to-one mapping between V adder and P adder, right? So basically you divide V adder into a virtual page number and an offset inside that virtual page, right? You convert VPN to PPN and then you add that offset. So this is the offset, this is called the page offset, right? So you divided V adder into a virtual page number and a page offset. Then you converted VPN to PPN using a lookup table, and then you computed P adder as this, right? You just dereferenced memory at that page and added the page offset to that, okay? If P is a power of 2, then these operations are very simple. V adder by P is nothing but V adder shift left by P bits, small p bits, right? And V adder percentage P is just V adder and let's say 1 less than P minus 1, right? So this gives you, it's a mask which has the last small p bits set to 1 and everything else set to 0, right? And so, and PPN into P is nothing but PPN shifted left by small p bits, okay? All right. So now the question is, how big should this capital P be, or consequently small p be? So how big should it be? If it's 0, if small p is 0, which means capital P is 1, then I have extreme flexibility in where I can place each and every byte, right? I can place each byte completely anywhere in the thing, but the lookup table, how big is the lookup table going to be? It's pretty big, right? Because for each byte I need an entry which maps it. So on the other hand, if I have P as a very large number, let's say P was equal to let's say P was equal to 10 megabytes, or power of 2, let's say 32 megabytes, okay? So let's say if P was 32 megabytes, then firstly I can so now my lookup table becomes really small, right? Because what's the size of this address space? It's 0 to 2 to the power 32 minus 1, which is 4 gigabytes, right? And the size of memory is also limited by whatever physical memory I have. So let's say if I had only 512 MB of physical memory, then the number of pages I'll have if I have a 32 megabyte page is 512 divided by 32, which is let's say 16, right? Okay. So 16 pages in the entire thing. So my lookup table is going to be just mapping 16 integers here to 16 integers there, right? So my lookup table is only going to need 16 entries if my page is that big. But the problem with that is, if most of my processes are really small, then each time I allocate a process, I need to actually allocate at least 32 megabyte of space, number one. So I'm wasting a lot of space in the middle, right? And okay, so here's an engineering decision to be made. What's the size of a page? Okay, and the typical size of a page that's used in modern hardware is 4 kilobytes. Right, so capital P is equal to 4 kilobytes and small p is equal to 12. So just 2 to the power 12. So we are going to, as we go along the course, we are going to see why, a number like this makes sense. It actually depends on the physical characteristics of the hardware, etc. But let's just first understand, assuming that a page is 4 kilobytes, how does this mechanism work? So a page is 4 kilobytes. What happens is a virtual address is 32 bits, of which the last 12 bits are called the page offset, and the top 20 bits is called the VPN, right? And similarly in the physical address, this is the PPN, right? And now I need to design a lookup table which maps VPN to PPN. So in other words, I need a mapping from 2 to the power 20 numbers to another 2 to the power 20 numbers in the most general case. So one way to do that is to have a table of 2 to the power 20 entries, right? So I could have one big table. Now let's call this the page table, which has 0 to 2 to the power 20 minus 1 entries. Okay, and I'm going to take the VPN and use it to index this table, right? And whatever value is stored there, that's going to be called my PPN. Okay, that's one way to do this. How big is this table? Okay, so each entry will need to be 32 bits, right? So that's 2 to the power 5 into the number of entries. Yeah, so into 2 to the power 20, that's equal to 2 to the power 25 or 8 MB.
Won't each entry occupy 40 bits, 20 bits for the source and 20 bits for the destination?
Okay, the question is, shouldn't each entry have 40 bits instead of 20 bits? No, because the VPN is actually being used to index the thing, right? And so you save space in that sense by doing this kind of thing. Another question could have been, why do I use this thing where I have a huge page table, where I am actually assuming that VPN can be used to index it? Why not have something more efficient like a linked list, which has all these VPN to PPN mappings, right? That's likely to be smaller in the common space, but it's a time to actually walk through that linked list that's going to become the bottleneck. So as you can imagine, you're going to actually do this translation on each and every memory access, and so the most important engineering decision you have to take is basically to minimize this translation overhead, right? So you want to minimize the translation overhead. It doesn't matter, space can be optimized in other ways if possible. Okay. Why is the PPN 32 bits? It could have been 20 bits, right? But 20 bit, the memory itself is byte addressable, right? So if I say it's 20 bits here, then the address of the first entry becomes 20th bit, and so it doesn't make, I cannot access a bit in memory. I can only access memory at granularity of a byte, number one. Okay, you could say, oh, why does it need to be 32 bits? Why can't it be 24 bits, for example, right? Which is 3 bytes. Well, that's possible, but actually that also complicates hardware. It's better to actually have power of 2s. And the other thing is, you actually use the extra 12 bytes for other purposes, extra 12 bits for other purposes, which we're going to discuss later. Okay, so that's a lot of space. So that's like, let's say this is 2 to the power 32 MB, right? I'm getting it right? Okay. So 32, hold on. So this is 2 to the power 2, right? So 4 MB, right? That's 32 bits, which is 4 bytes. So 4 MB of space. So clearly 4 MB of space cannot be allocated on chip, right? Well, we said chips can only have some registers which are few tens to hundreds of bytes. So 4 MB of space cannot be allocated in chip. So this data structure has to live on memory, right? And but if this data structure has to live in memory, you are saying that every process will have its own page table, because every process will have its own virtual address to physical address mapping. So every process will need at least 4 megabytes of space to at least store the page table. Typical process sizes will be few hundred of kbs to 1 MB to 10 KB. Things like processes like grep and ls and all these are very small processes, and if for every process I'm actually creating a page table that's 4 megabytes of size, that's a lot of wastage. So what's done is basically you divide the page table into a 2-level page table. The first level is called a page directory. And the second level are called page tables, where each of these entries in the page directory points to a page table, and so on. Okay. So once again what I do is I look at the VPN and I take the top 10 bits of VPN. So let's say VPN bits 31:21, let's say 22 to 31st bit, and we use that to index the page directory. I get some address. This contains the physical address of the page table, and then I look, and then I use VPN 21:12 to access the corresponding page, and so I get a page, and then I use VPN 11:0 to offset into the page, right. So what I've done is I've divided the page table into a 2-level hierarchy, right. I said why not just have a list or a tree to store this, and we said having a list or a tree is actually going to increase complexity of hardware, but at the same time you need to strike a trade-off between how complex the hardware needs to be and how much space you are allowed to waste. And so the designers thought, let's just divide the table, this large table of 4 MB, into a tree of tables, but allow the tree to be must be of size 2, okay, or depth 2. So in this case I was using 20 bits to index into this page table. In this case I am using the first 10 bits to index into the first page directory, and using the next 10 bits to index into the second page directory or page table. Okay. So this way if I have a process which is actually taking only let's say 100 KB of space, so it only needs 0 to 100 KB mapped in the address space. So what will happen is one or two of the entries here are going to be filled, and all the other entries are going to say they are not mapped, right, and that way you save space. So only 1 or 2 entries are filled in the page directory, and you only have 1 or 2 page tables in that case, and the total amount of space that you are using for this page table structure is, let's say, three of these, right, one here and one of each of these, let's say 2 of these, or one or 2 of these, depending on the size of the process. Let's see what the size of the page directory itself. I'm using 10 bits to index into the page directory. So how many entries does it have? 2 to the power 10, right? And how big is each entry? Each entry contains the physical address of the page table. And how big can a physical address be? 32 bits. So it has, but a physical address can be 32 bits, but you have also segmented the physical address space into pages, right? And so the number of pages you can have in the physical address space is 2 to the power 20. So really each entry needs to be 20 bits, right? Each entry needs to be 20 bits. And so, but once again 20 bits is is not a very nice number. So we extend it to 32 bits, and so it becomes 32 bits is 4 bytes, right? So it becomes 4 into 2 to the power 10, which is 4 KB. So that's the size of the page directory, and interestingly, that's the same size of the page, right? So a page directory itself lives on a single page. Similarly, what's the size of the page table? Same thing, right? You're using 10 bits to index in the page table, and each entry is 4 bytes, so it's 4 KB again. So once again, the page table itself lives on a single page, right? And then you use that to index a page, and you get the page. Okay, all right. So let me just review this. This is the virtual address VA. You divide it into 10, 10, and 12. Was 32-bit address. You use the first 10 bits to index into a page directory. I'm going to call it a PD, page directory, and you're going to get a PDE, page directory entry, using this. You're going to get the contents of the PDE to dereference a page table. Let's call it a PT, and you're going to get the next 10 bits from here to index into the page table. I'm going to get a page table entry, right? And now you're going to get a page from here finally. You got a page, and you're going to use the last 12 bits to index into this page to get your final physical address. Let's see how this works on x86. So x86 actually uses both segmentation and paging. All right. So virtual address of the form segment colon offset. This is called a virtual address VA. Goes through the segmentation hardware, as we discussed earlier, to give you another address, which we have been calling the physical address so far, but actually gives you what's called a linear address. All right. So let's call it the linear address. Linear address. The reason it's called a linear address is because now this address has no segment colon offset. It's just one number, which 132-bit number, right? So it's a linear address space. And now this goes through paging hardware to give you a physical address. Okay. So it gives you both. An operating system is free to use both. An operating system is free to use only segmentation, in which case all it needs to do is disable paging. All right. So how do you disable paging? It has certain registers which are called control registers. CR0 control register 0, CR1, CR3, let's say CR2, and maybe more. And you know there's a bit in CR0 which says enable or disable paging. If you disable paging, you're only using the segmentation hardware, and that's likely to be quite fast, right? Because you are not going through the paging thing, which involves looking through the page tables. But actually, I know as we're going to discuss later, paging is also not all that slow, and you know there are ways to make that fast. And this is basically what's typically used. It has advantages. So an operating system is free to use only segmentation, or an operating by disabling this bit, or an operating system is free to use only paging, right? In which case, what does it need to do? You know, all it needs to do is basically set all its set its segment selector that we discussed in our first slide. Okay, so all it needs to do is set its set all its base and limit to 0 and 2 to the power 32 minus 1. Right? If in all its segment descriptors it sets its base and limit to 0 to 2 to the power 32 minus 1, it's effectively disabled segmentation. Okay. So in the next few lectures, I'm going to assume that the base and limit have been set to 0 and 2 to the power 32 minus 1, which means the virtual address is equal to the linear address. Okay, and most operating systems actually do this, right? So most operating systems like Linux, Windows, and the operating system that we're going to do in this class, which are XV6, BIOS, and PinTOS, will all set base and limit to these values, and so only use paging for implementing virtual memory. Okay. What is the use of having segmentation? Well, the hardware designer has given you a choice, basically, right? And the hardware designer designed the hardware before the operating systems were written on it. So there was he basically tried to say that I don't know what the operating system may want in future, and so he designed it, and because of backwards compatibility it remained in the hardware. In fact, on the 64-bit architectures that have come up recently, segmentation is not present, so you don't have segmentation in this form. It's a very, very thin form of segmentation that you need, because most operating systems are not using segmentation. Okay, all right, so I'll stop here, and we're going to discuss more about paging in the next lecture.